Okay, in practice 8, we're going to look at deep neural networks. We're going to, I mean, it's building on what we did in the last unit on neural networks. But we're going to expand it and also look at some ways to add more layers and optimize the learning for these layers. So we start with section 0 here, which in previous ones, again, we just import a lot of libraries. And again, we're now using these Keras libraries. These are for our neural networks. We have our sequential neural networks and each type of layer we might use, and some other methods in here. So this is kind of the new one in the last couple units for neural networks. I want you to go and we're going to look at the digit challenge from Minst. Basically uses the Minst data, but it's from Kaggle. So if you click on this, it'll bring up the challenge here. I want you, hopefully in the last unit, you did a submission here. So you should be able to scroll down and see what your last score here is, and then just record what your last score. And our goal is, again, to bring that score up a little bit now. So I want you just to record your previous best score here, so you have a record of it. Now let me close this section. In section 1, we're going to do a lot of things. And the idea in this notebook is you're going to go through section 1 a number of times and make a number of changes in it. Rather than duplicating this section multiple times, I decided to kind of set it up. So the idea is that, let's just go through it. You read in your data here. You set up your data into training and testing areas and get things set up with one-hot encodings and stuff like that. And then you set up your neural network here. We will then compile the neural network and set up some what are called callbacks, and then we'll do some training. We'll fit the neural network. This will be our training, and then we'll evaluate how it's doing. We can also plot the neural network and how it's performing. And again, when you're fitting your neural network here, we'll run through different epochs, and then this will take a while. So here I have a relatively simple network, and it only has 10 epochs, and it's going relatively fast. But again, we typically do this for 100 epochs. And again, as you get more complicated networks, this can take longer. So just be aware that this will run for a while. And again, we're watching these graphs of our training accuracy and our loss, and talk about those. So the idea is that, and then section 2 is where you actually create a submission to Kaggle. So the idea is that you go through section 1, get a good set, and then maybe decide to submit this to Kaggle and do section 2. But you'll probably want to go through section 1 a number of times before you submit something to Kaggle. So there are a number of tasks in here. And they're not all in order, but I want you to do them in order. So like task 5 is up here, and then task 3 is down here and stuff. So what I want you to do is start at section 1, go through, run these cells, and find, you've already done task 1, which was up here in section 1, where you did the Kaggle result. So now I want you to go down and find task 2. So run the cells down here until you get to task 2. So here's task 2, is to work with deeper neural networks. The traditional neural network is there's 3 layers: an input layer, a hidden layer, and output layer. And then in our first unit, we actually used 2 hidden layers, and now we want to look at multiple hidden layers here. I'm going to modify this one thing. So here's a network that has 50 units, the input layers here, and then we have 50 units in the first hidden layer, and then 40 units, and then 30, and then 20, and then the output layer here, and that's what is called a softmax layer, and that will try to activate a single cell output. And again, we're predicting digits, so again, this is going to be 10 units. Output size is going to be 10 here, and then we have about 700 input units here. Now the art of crafting these neural networks and choosing a network size and stuff, there's no great science to this. There's lots of different ideas and suggestions, and in the coming weeks, we'll look at some actual structures for these networks. But in a traditional neural network, there isn't a lot. One of the guiding principles is that you'll start with small detecting small features, and you'll have a lot of them. So maybe in your images you'll be detecting lots of edges or stuff like that. So we start with 780 pixels, and then we feed that in, and so your first layer should probably have a lot of nodes to detect lots of small features, and then we'll want to refine that and build more complicated features up. And so we usually do that by forcing that network to get smaller and smaller in size. And so we're going to try to encode in 20 units all the information that was in these 784 pixels, and also all the information that was in these 50 units. And then our final output is 10 units there. There's some argument that people make that you should actually have one of your hidden units, the final one, maybe less than this, so it's generalizing things, but there isn't any strong, again, it's an open area of discussion among neural network designers. So again, I wish I could provide you more guidance here, but it is an open area of how you set this up. But this is a typical structure, and I want you to try out some things. Later on, we'll put in this dropout unit here, and we'll talk about those in a future task. And I just had that left over here, so that's why I commented it out. So again, you go in here. So this is, of course, just the comment. This is where you'd actually change your code, and you can add or remove whole units, whole layers. Only thing you have to watch is this first line here has to have the input set, and then the last line has to be the output line. And then all the other units will automatically sequential, so they all automatically get input from the layer before and send its output to the layer after this. So for 2, I want you to do that. Try that. So again, you can try some different networks, and then go down here, compile the network, and again, we don't have to worry about these callbacks too much, but here where we fit the network, we can be doing some fitting of the network here. And then we can watch our training. And again, what we want to do is we hopefully want to see our training accuracy increase to 90, 99%, something like that here. And our loss function should go down for this. Now, if you want to try and change this again, if I just go back up, if I just change this network structure here, like I took out that 30, and then I rebuild this. I rerun that layer. I recompile the network, and then I can retrain the network. So it's going to go through right now. Again, I'm only doing 10 epochs. And again, I should see the accuracy start relatively low and then go up. So it's starting relatively low here and should increase from that. This is the result after the first training. So even after the first training, going through it, it's able to get up to 88%, but then it should increase. And again, I should see my graph look something like this, and you can see how high it goes. And we're going to watch both the training and the testing, and we'll talk more about that in just a sec here. But I'm getting up to 98%, and again, I can run this for more epochs. So you should probably be running this for maybe 100 epochs at times to see if you see improvement there. Okay, so task 1 is to try out some different network sizes and stuff here, and try to get a set of layers that you think performs pretty well. You can also be doing that was task 2, because task 1 again was just the beginning report of your initial score at Kaggle. Task 3 is to look at the learning rate here, and this is how fast we learn, and we had a fair amount of material about this in the early part of the chapter, the learning resources here, but I've duplicated some of that here to remind you. So we can set the learning rate, and again, we want a learning rate so that it finds the local minimum. And the idea is here is that, like, if we're at this point and we know we want to find often the lowest point of loss here, we'll move this direction. And again, if your learning rate's too large, you can move here and end up over here. And again, sometimes that's not bad. You can still get down to this lower learning rate. But if your learning rate's too bad, if you're moving this direction, you'd actually go way over here and bounce around a lot. But if your learning rate's too slow, again, you can get trapped into a local minima and not be able to get out of that. So one of the ways we do this again is we start with a relatively large learning rate and then we shrink it down. And this uses these callbacks. So we have this reduced learning rate on plateau callback. We're going to monitor the accuracy of the model. And this is the important thing. The factor is a third. So basically, if the learning rate starts at 10, it actually is some small fraction, but let's say it started at 100, and then we wanted to reduce it. We'd multiply it by zero point 0.3, and so that from 100 would go down to 30. And then next time we reduce it, we'd go from 30 down to 9. Again, multiply it by zero point 0.3 for that. And although the learning rate usually starts at, I think the default learning rate is 0.001 or zero point 0.01. So it's a relatively small amount every time. But again, we're still shrinking each time. And this is the smallest it's going to go here as minimum learning rate. And the patience is how quickly it will change its learning rate. So we define that callback there. And then here, when we do our fit, we've added this callback thing, and we've added the callback there. Another option you can have is sometimes it's hard to know how many, if you should run this for 100 epochs or more. You just want to run it till it isn't learning anymore. So one thing, if you do have 100 here, you can put in this early stopping here, and that's another callback here. It's going to monitor the accuracy, and if the accuracy doesn't change for like 6 epochs, it will automatically stop this and won't train anymore. So this is good, especially when you're running a large number of epochs, to have this early stopping in here. There's also, you can also save the model weights here as you go. We'll talk more about that a little later. But when we get to bigger models and you can't train the whole thing here, sometimes it's nice to save the weights. I guess I will mention it. It's actually way down here. I will mention it again. Is that these commands can save the weights to a file and load the weights from a file. And so again, if you need to quit for a while and you have a really good network that you trained for an hour or two, for example, you can save those weights and load them in later on. This will be even more important later on when we have larger networks here. You have to watch here. It's saving it to the cloud here, and it'll probably show up in your files area. You may have to then download it in your computer so you can have that. But there are options to save the weights and load them in later on, but it's not very critical here. Okay, so back here, we've task 2. Maybe while you're doing your learning rate, you can also look at reducing the learning rate here. There's just some questions here you have to answer concerning the learning rate. And same with the other callbacks. Answer these questions about the other callbacks. And then look down here and see what callbacks are actually being used in this area. So that's the first 4 areas. And again, our idea is then to run this, try to go through this a number of times, try to get the accuracy up here until it's at a good level, and then create a submission and submit this to Kaggle. One thing you'll see is that even though your testing might show, that you're up at 97% or something like that, the actual testing data Kaggle has is different and sometimes a little more challenging. So your results for Kaggle may be a little different. So when you submit them here, you can submit your predictions. You can check your score out and see how closely it matches. Okay, then the last task in here is to look at fighting overfitting. So what happens is, especially if you have a number of layers here and larger layers here, your network can memorize all the input data, and what you'll see is your this training, the blue training line will hit 100%, and here your training accuracy will hit 100%, and then your loss will drop down to 0. And when your loss drops really low, you're not actually learning at all here. But that's just on the data, the images, the digit images that the network sees, and it can memorize those basically. And So we've got some data set aside for testing data, and that won't be at 100%, and it'll often get worse as you get close, as you train more and more. And so sometimes you'll see this. What we want to see is both the training and the testing line to slowly increase and the loss to slowly increase over time. And what you will see at times is that the training data will go up and up and up close to 100, and then over time this testing data will plateau and maybe even drop down. So you may be only recognizing 94% of the digits with the training, with the testing data, even though your training accuracy says you're on 100% of the time. And then again, if you submit to Kaggle, they have a whole separate set of data they're testing you on, and so you might have a relatively low score even though you think you've trained very well. So that's kind of overtraining, or what we call overfitting. So one thing we can do, a couple things we can do with that. We can have the model save the best weight. So there is one of the callbacks you'll look at is we'll save the best training performance so far. But that only goes so far. What we really want is the network to generalize and learn some generalized rules here. So there's something called dropout layers here. So again, right up here where we define our network, right below that is this task 5, which we skipped over. See, it says, please do tasks 3 and 4 before this. And this talks about overfitting and asks, do you have overfitting? Are you seeing that? And try some dropout layers. And so again, we put in a dropout layer in here. And what that does is this layer will randomly ignore, in this case, half of the connections from this layer. And it will force it to kind of strengthen the connections and rely on certain things. It's kind of like if you were trying to just do this visually and look, you're looking at the images with two eyes. You might close one eye, and you might close your right eye and use your left eye, and that should strengthen the left eye's performance. And then you might close your left eye, and that would strengthen the right eye's performance and the neurons in your right eye and the left eye. And kind of like that is that we're randomly shutting off parts of the network to help increase the learning in the other parts of the network here. But this can also cause problems. Typically, they do a drop up of 50% here, but that might be kind of high in this area. So I can add this, and again, often we add drop-off layers between each of the layers. So again, I could do a drop-off layer right here. And then so we have the input goes into the first layer 50, and again I can change the size of that. Then I have a dropout, and maybe I'm only going to drop out 20% of these, and then I go into a layer of 40 network nodes, and then again maybe I drop out another 20%, and then I go into and again, this is just randomly shutting off some of these connections from this layer to this layer so that it will help strengthen the other connections. Now, this works only during training. When it does testing, it actually will turn off the dropout layers because we don't want those during testing. And so those will only work when we're training the network. So again, you can redo this, run that, and then go down here and run these other lines. Recompile this. Now here I'm getting an error in the compile. Apparently I missed the compile line up here. So let's go up and find that. And again, sometimes if you make a mistake in your network, when you compile it, you'll get an error. So now I'll run my fit, and again I should be running this for more epochs, but for this video I'm just running it for a couple. Okay, it's just finishing up here, and then I can again do my evaluation, or more importantly do my graph here. And what I'd like to see often is that the accuracy may not increase as much as it did before, but the validation accuracy, this is run on the separate testing data we have, that should increase higher, because again we're not doing the dropouts there. And so here we're actually seeing the testing accuracy at a higher amount than this, and so you can play with that. And so again, that's working with that. So again, we wanted to see our testing accuracy is actually above our training accuracy, because the training accuracy is working through those dropouts. It's got that noise in there where it's losing connections randomly there, and so it's trying to do its best and strengthen other connections, and so our testing accuracy is actually better there. So try that. Try some different dropout layers and see. And again, your final goal is to submit your best value here to Kaggle and record. So record your initial score here and your best score here. You should be able to see those. Kaggle will keep track of your scores. It doesn't show them in order. It just shows them, again, usually in order of submission. So hopefully you'll have a good score here. And again, you'll probably have some poor scores here. Okay, so that's the challenge for this practice.